Hey guys, this is Leetcode number 64. This problem is called unique paths. First I'll go over the problem, then I'll go over the implementation and solution, and then I'll go over what the code looks like. So let's go ahead and jump into the problem. So the problem basically says that there's a robot located on the top left hand corner of an m times n grid. It's marked start here. And basically what you're supposed to do is try to figure out how many different paths the robot can take to get to the finish line. The example that they kind of give you is a 3x2 grid, and they output the number 3 because you can go right down. Let's just go over what that would look like. So they're saying that they're giving you a 3x2 grid. So that kind of looks like this. And they're saying the robot is here. And this is the end. Right? So they're also saying that the options that you currently have right now is to either go right, down, and right. So that's one option. Another option you would have would be to go down, to the right, and then another right. Oop. Another option you would have is to go that way, right? And then the third option that you kind of have is to go to the right again, and then go right again, and then down. Right? So those are your three options that you kind of have. Those are your three paths. So this problem is kind of interesting in the sense that you first look at it and you're kind of like wondering to yourself, like, how could I possibly solve this? So one of the ways that I came up with it right off the bat was to either use like breadth first search or depth first search, right? To basically try to find as many paths as possible and then to see which path would end up leading towards the end. But the problem here can be solved by using DP. I know DP, dynamic programming, can be kind of hard to understand, but I'll walk through what the solution kind of looks like using DP, and it's kind of easy once you get the hang of it and once you understand what it's trying to do. So we'll use a little bit more complicated example than what we were given up there, just because it's a little bit easier to understand with a bigger graph. This is where our robot is, and this is where our end is. So this is going to be a 4x3 grid. 4x3. That means m is equal to 4, n is equal to 3, right? So they're asking us to figure out how to get to the end. So now we know that however many steps that you could possibly have here would be a combination of however many steps you had here, right? So steps here is the same as steps here minus 1, right? Same as this one. So whatever the steps here would be, you're just subtracting whatever the steps here was. So to illustrate that, let's just give it a random value, right? Just for the sake of example, I'll just say this is 1. And I'll say this is 1. So that basically means the robot can take one step here and one step here. That's just how many steps that they've done so far at this tile, right? In fact, in this problem, you can pretty much fill out the top row with 1s, right? So all of these are 1s and all of these are 1s. So now let's try to figure out how many steps there are to here. So we know that the steps to get to here would be a combination of how many steps would be here plus however many steps here, right? Because to get to here, you can either come from this path or you can come from this path. Those are the two different paths that you can end up here, right? Because you always want to either move to the right or move down to get to the direction that you're trying to go to here, just because it's the end index is here. So basically this right here would be a combination. I guess you could write this out Okay, let me change my ink. Would be if this is 1 1 right here, right? So 1 1, so you can say like dp of 1 1 is equal to the dp of the one above it, because we said that one of the steps that you can get to is from this direction, right? So the one above it is going to be 0 1 plus the one to the left of it, which is this one right here. So this one would be dp of, this is going to be 1 0, right? And we can kind of follow this all the way through, right? As long as we start at this, we can figure out what the ones before are. And that's kind of how like dynamic programming works. You figure out the steps before, and then when you get to the certain step that you want to try to solve for, you basically refer back to the steps that you've already solved. So that's what we're doing here. We are referring back to the steps that we've already solved and trying to figure out what the solution was before. So in DP, once you figured out basically what the formula kind of looks like to repeat your steps, it's pretty much easy to figure out what your function and method is going to look like. So we've already done that part here, right? We figured out what our formula is kind of going to look like, which is this. So now let's go ahead and fill out the rest of this array with ones. The reason why we're filling it out with ones is that's just a default value that we're giving these columns and rows, so that when we start, we can kind of just do an addition of it. You'll see that as we go through our DP, our array, these ones will get replaced with the correct value that we're trying to load for. So here, so let's start here. So if we follow the DP method or DP function that we've written down below, it says that that whatever the value is here is an addition of these two. Right? It's going to be whatever this is and this is, which in this case ends up being 2. So let's go ahead and write 2 here. Right? And then let's follow that to here. So here it would be 2 and 1, which is 3. And so let's go down here. So in this case it'd be 2 and 1, which is 3. So in this case it's 3 and 3, so 6. So in this case you're looking at 1 and 3, so 4. So when you get here at the end, you're looking at 6 and 4, so that's 10. In fact, that ends up being our answer, because this is the actual thing that we're looking for. We're looking for m-1 and n-1. These are the coordinates that we're looking for, which is what this is, right? That's just what it ends up being, because that's the length of the array. So let's go ahead and take a look at what the code looks like. So I've already started writing out the code for this, and right now what I have in front of me is the method header as well as the definition of what the DP array is kind of going to look like. It is the length of m times n right now. So the first thing that we need to do is go through and fill up the array with ones like we did in the example. So I'm going to go ahead and do that here. So int y is equal to 0 and y is less than m, and then we're going to do y plus plus. And since we need to do it for the matrix, we're going to do the same thing here. Quick key here, randomly. Make sure that you call whenever, it might be a little bit helpful for you to call your coordinates for a matrix, x and y. It just helps me try to get through a matrix a little bit easier. So remember which coordinate to increment. Okay, so this is going to be dp of y and dp of x. It's going to be equal to 1, right? And that's it. In fact, we're kind of going to be doing the same thing for the next part. So I'm just going to duplicate it. Except this time, we're not doing this. What we're going to do, this is where a dp function that we came up with before goes, right? It's going to be equal to, so dp of y minus 1 x. So we're reaching to the thing that's 1 above it, right? So this is what this is. This is what this is. Plus, plus dp of the 1 to the right. And that's it. That's pretty much the entire code. You're pretty, at the end, you're just returning dp of m minus 1 and n minus 1. That's it. Hopefully you guys understood what I was saying here.